36 is a pretty interesting number. It is a square 6 times 6, but it is also a sum of all the whole numbers from 1 to 8, so it can be arranged as pretty steps. Every kid watching the British show Numberblocks knows this. Is there any other such number? Well, the number 1 is a trivial example, but you will be searching for a while and a bit longer until you find that 1225 is another one. So what is going on? The seed to the next number of both the step squad and the square club is already present in the previous member. You and I will now employ an important technical recursion to find a formula that generates all the members. Let's get started. First, let me show you how I computed the next member 1225. We will need the difference between the length of the steps and the base of the square for the number 36, which is 8 minus 6, or 2. The same difference between the length of the steps and the base of the square for the next member can be obtained as twice the previous base 6, plus the previous difference 2, which is 14. Finally, the base of the square of the next member is twice the new difference 14, plus 1, plus the previous base 6. Squaring this new base leads to 1225. Whoa! Where have these formulas come from? We are looking here at a square having a base of a that can be arranged as steps. Again, every kid watching Numberblocks knows that a square is a sum of two steps. We need to take the second step, having a minus 1 times a over 2 blocks, and rearrange them so the first steps can continue. We will make a tower of a plus 1, then a plus 2, and so on until a suitable a plus n, where n is the difference between the length of the steps and the base of the square that we have already mentioned in our formula. The steps that we have added have n times a plus n times n plus 1 over 2 blocks. Hence, a square that can be rearranged as steps has the property that there exists a whole number n such that a squared equals a plus 2 times n times a plus n plus 1 times n. For example, for 6 squared, there is n equaling 2 such that 6 squared is equal to 6 plus 2 times 2 times 6 plus 2 plus 1 times 2. Indeed, 2 is the difference between the length of the steps a, which we are hoping to construct, and the base 6 of the square, from which we are making the construction. Let me visualize the key property. The base a must be made of 1, 2n, and an unknown whole number b. We will now show that b squared must be either a member of both the step squad and the square club that is smaller than a squared, or that a squared was the trivial one. Here we see the recursion. To find the base of the next member of both the step squad and the square club, we can utilize the already obtained one, given we first compute the difference n. Remember that the rectangle a times b must have the same number of blocks as n plus 1 times n, which is 1 plus 2n plus b times b equals n plus 1 times n, or 2nb plus b squared plus b equals n squared plus n. Let's focus on how many times b may occur in n. I mean, we are going to really dissect this. First, b clearly cannot be bigger than n. Do you see it? Good. Second, if they are equal, then this is only possible if they are equal to 0. In such a case, we end up with the trivial case of a being 1. If b is smaller than n, then geometrically we see that it must be at least twice smaller. If it is precisely twice smaller, then b must be 1, and a squared is the next member of both the step squad and the square club, which is 36. Finally, here is the geometry of the last case of n equals to b plus m, where m is a whole number. We cut away the areas from the rectangle a times b that we can find in n plus 1 times n. We end up with b squared being equal to b plus 2mb plus m times m. But this is exactly the same relationship between b and m as we had between a and n, which makes b squared arrangeable as steps of a length of b plus m. Now we summarize. We have first assumed that a squared can be rearranged as steps of the length a plus n. Then we have discovered that either a squared was the trivial one, or that there was a smaller b squared that can be also rearranged as steps of the length b plus m. This recursion must end, and naturally it can only end with the trivial case. This technique is also used a lot to show that something does not exist at all. That would have happened should there was no trivial case. Going backwards, writing formulas how from b and m we can obtain a and n, we will be able to generate all the members of both the step squad and the square club. Enjoy!